Hello everyone, my name is Shubhendu Behra. I'm a recent master's graduate student from NC State University. On behalf of me and my co-authors, I'm going to present our paper titled Orchestrating Fault Prediction with Line Migration and Checkpointing. So we will start with some background, then we will go through the system modules and the checkpoint restart model, followed by evaluation and summary. As it is already known that failures and IO performance degradation are two of the biggest challenges in the SPC domain. They lead to bad application performance. As can be seen in this table, some of the biggest SPC systems suffer from low mean time between failures, which is in the order of days. At exascale level, the mean time between failure is expected to be in the order of hours or less. The second problem of IO performance degradation is due to high parallelism and the increasing latency gap between computation and the parallel file system IO. One single checkpoint can take in the order of minutes. Checkpoint restart is widely used for providing fault tolerance in the SPC domain. For it to be successful, it requires efficient handling of failures while committing the checkpoints faster. Keeping that goal in our mind, we propose our solution, a multi-level checkpoint restart model that orchestrates and combines multiple fault tolerance techniques while leveraging modern storage hierarchy. Our checkpoint restart model integrates a failure prediction module that predicts a failure with the lead time and the node on which the failure is going to happen. It takes proactive actions such as live migration to minimize the recomputation overhead. We also make the checkpointing with the efficient use of burst buffers. Our evaluation is novel in that it uses the failure prediction module outcome such as failure prediction location and the lead time based on system logs instead of relying on statistical models. Our study shows that both burst buffers and live migration technique are synergetic in improving the efficiency of checkpoint restart solutions. The first module in our system is the burst buffers, which act as an intermediate buffering device to reduce application IO blocking while providing better latency. There exists many architectures of burst buffers. Our checkpoint restart model focuses on the local burst buffer architectures. We utilize the burst buffers to store the checkpoints and asynchronously bleeding them off to the parallel file system while execution of an application continues. We also optimize this process by limiting the number of writers on a single node. Further, we optimize the recovery process by mandating the new replacement node to recover the checkpoint data from the parallel file system, while other nodes recover the checkpoint data from their burst buffers. The second module in our system is the live migration, which is a mechanism to relocate processes on a vulnerable node to a new and healthy node. Here we make several assumptions. First, we assume that processes continue to execute while live migration is under progress. Second, the cost of loading an application on a new node and making necessary MPI runtime environment changes is minimal. Finally, the amount of data that needs to be transferred for live migration is bounded by the DRAM size. Based on these assumptions and the internode bandwidth measurement experiments, we find that it takes 41 seconds to perform live migration on Summit. The third module in our system is the failure analysis module. In this module, we leverage the DESH model to analyze the logs of 3 modern SPC systems over a period of 6 months. In this analysis, we find out all the instances of common sequence of phrases that may lead to a failure. We consider those instances as faults in our simulation. We calculate the lead time for each failure as the time difference between the final phrase and the first phrase. For simulation, we consider the mean lead time for each type of failure, and based on that, we find that 44% of the failures can be mitigated with the use of live migration when we consider the mean lead time. All these 3 modules are coordinated and orchestrated through failure prediction. Our failure prediction module orchestrates live migration and checkpointing by taking the inputs from the failure analysis module and it utilizes the burst buffers for efficient checkpointing. Moving on to the checkpoint restart model, our decision making in the model depends on the factors such as failure prediction status, which states whether a failure has happened or not, node type, whether the node is a new node or one of the old nodes, failure type, whether the failure that happened was a soft failure or a node failure, and the available lead time. With these factors, we start with the question, has a failure happened? If it has, then the recovery process depends on whether a new node was added. If the failure was a node failure, then the checkpoint data for the new node can be recovered from the parallel file system. For soft failures and for other nodes, the checkpoint data can be recovered from their local burst buffers. If a failure has not happened, then the next action is taken based on the failure prediction status. Without failure prediction, the checkpoint model follows the preventive checkpointing method to store the checkpoint data on burst buffers and then asynchronously bleed them off to the parallel file system, following the optimal checkpoint interval formula using Young's formula. If a failure prediction has happened, then we rely on the prediction lead time to take the next action. With enough lead time, we can take proactive live migration action and migrate the processes from the vulnerable node to a new and healthy node. Without enough lead time, the failure could be imminent. For evaluation, we built three models. Model A, which is the base model. Model B has the assistance of the burst buffers. Model C is an upgrade over Model B with the assistance of failure prediction module, failure analysis module, and the live migration. This is our model. For our experiments, we simulated a run of 6 real-world applications on an emulated platform of Summit, and the requirements of those applications are diverse in terms of nodes, checkpoint size, and runtime hours. With our checkpoint restart model, we were able to achieve a 20 to 86% reduction in overall application overhead. Figure on the right represents the normalized application overhead for all three models. Each bar represents one model, with model A on the left and model C on the right. Further, each bar is stacked with different kind of overheads, such as checkpoint overhead, which is the time duration during which an application is blocked to commit a checkpoint. Recomputation overhead, which is the time loss or computation time loss because of failures, and recovery overhead, which is the time required to recover an application from failures. The overall reduction in checkpoint overhead is around 29% to 87%, with lower residual failure rate contributing 5 to 29% reduction, while burst buffers contribute 30 to 82% of reduction. However, burst buffers do not contribute for S3D application because of equal parallel file system and burst buffer bandwidth. The reduction of recomputation overhead differs for different applications in terms of size. For larger applications, the reduction is around 51 to 56%, whereas for smaller applications, the reduction is from 13 to 85%. The burst buffers contribute a 29 to 83% reduction of recomputation overhead for all the applications except S3D because of the equal bandwidth for PFS and burst buffers. The reduction due to live migration also differs for different size applications. For larger applications, the reduction is 13%, including the S3D application. For smaller applications, the reduction is 2 to 14%. Further, because of the reduced failure rate, there is a 29% reduction in checkpoints, which effectively increases the longevity of burst buffers by 41%. In summary, we developed and evaluated a multi-level checkpoint restart model that orchestrates live migration and checkpointing with the help of a failure prediction that takes input from a failure analysis model. It also improves the checkpointing method with the use of burst buffers by reducing the PFS contention with asynchronous checkpointing and an efficient recovery process. With our model, we were able to achieve a 20 to 86% reduction in application overhead while increasing the burst buffer longevity by 41%. Finally, we would like to thank our sponsors for this project and also thank our reviewers for their invaluable inputs. Thank you.